In tutorial 5, question 1, you're asked to run set up and run a simulation for some statistical properties of the OLS estimator in a regression. And what I want to do in this video is just to go through step by step how you take a question like this and turn it into a simulation. So one of the things that will strike you when you haven't done this before and you read a question like this is there's a lot of information and how on earth do you make sense of this and turn this into a simulation that answers the question. So rather than simply giving you a completed answer, I'm actually going to go through step by step, starting from a blank screen, how you build a simulation to do what this question asks you to do. And hopefully that will be helpful. So first of all, let's pick through the question. Now what I suggest you do, by the way, to make the most of this video is to kind of treat this as your part A preparation for the tutorial. Is don't just sit and watch this all the way through. Rather, as I go and put in commands into R one by one, is you should pause this video and do the same and make sure that you can follow what I'm doing and make sure that it works, and so that by the end you will have a program that looks like mine, and you'll pretty much have this question 1 sorted out actually. Alright, so let's have a look through this question. First of all, you're told that we have a PRF. This is standard kind of stuff. We have a PRF in which we have some explanatory variables including an intercept and 2 explanatory variables, and we have a vector of regression coefficients called the usual things, so nothing unusual there. Then, here are the details of the simulation, and all of the detail here is important, and you need to know what to do with it. First of all, you're told that we have an IID sample. That's all that we've dealt with so far, apart from that single AR1 example. So everything else has been IID, so that's not too difficult for us to deal with. We've seen examples of that. It's more difficult when we don't have IID. We'll come back to that in a few weeks. Now, we're also told, this is additional information, that the 2 x variables together are normally distributed. So that's telling you when we're going to do a simulation, we're going to have to use something like that rnorm command that we've seen before in order to draw samples from the normal distribution. But there's an additional complication here, an additional extension, which is that we now have 2 of these x's. Each of these x's have a mean of 0, and they each have a variance of 1. And here's the interesting bit. They're correlated with one another with some correlation coefficient rho, which can take the value 0.5. Well, later on in the tutorial you get to change the value of rho. And it's this correlation that we need to deal with. So let's just make a note of that, and we'll come back to that. You're then told that the conditional distribution of y given these 2 x's is normal. This is the same kind of situation that we've seen before. So we're still just sampling from normal distributions. With the nice mean function, we've got the true regression coefficients here. 0, 1, 1, okay? 0, 1, 1 are the true values, the population values. And this conditional distribution has a standard deviation of 1. So we're getting some information there that we need to make use of when we're setting up our sampling process. Then you're told, so that's all the information about the population, basically. The population of the y's and the 2 x's are IID normal, the x's are correlated, the y's is related to the x through this regression function with these coefficients. Okay, so we need to use all of that information in our program. Then, when we do our simulation and we do our sampling, we need to draw a sample of size 50, so we'll set n is equal to 50, and we need to do 1,000 of them. It's telling you how big the simulation should be, and then ultimately the goal of this is to look at what are the statistical properties of one of these slope coefficients. Just the coefficient on x1 is going to be the focus of this. Alright, so let's go about trying to do this. Now, the first thing I would do, don't just sit down and try to write the simulation right from the start. That's too complicated, you get lost in all the details. So even when I'm doing this, the first thing that I'll do with this is to go through and observe that there's a whole bunch of parameters that are being told to us here. So let's just write those down. It helps to be clear in your mind if you get all these parameters down, and then you'll probably use them, but even if you don't, it doesn't matter. So let's start with well, I'm over the betas. Let's start with the betas. I'm just going to write down what those betas are. So beta 0 is 0, beta 1 is 1, and beta 2 is 1. I'm just going to put those into a program. So let's go into RStudio and a new script. And so I'm going to put in here beta 0 is 0, and beta 1 is 1, and beta 2 is 1. Okay, put that there for safekeeping. All right, what else have we got? We've got a correlation coefficient of rho, which is 0.5, so we'll put that in. And we've got a sigma is equal to 1. Let's put both of those ones in. So rho is 0.5. That's a habit and from other packages. And sigma is 1. I've put a blank line there, it doesn't matter. Put all those coefficients together. Alright, what else? We have a sample size, we can put that in, and we have a number of repeated samples, so I might put that in, and I think that would be just about all of the... Well, we've got these means of zeros and variances of ones for these x's. Now if you look ahead in the tutorial, those two are not going to change, so we could put in, you know, mean of x1 equals 0, mean of x2 is equal to 0, and so on, but I actually won't do that. But I'll put in the n and the replications, so I'll just put in here n is going to be 50, and actually I'll leave the replications for a minute. I'll come back to the replications because a good thing to do when you're setting up a simulation to begin with is not to try and do 1,000 replications right from the beginning. Just do one. Make sure you can do one and then worry about the 1,000 after that. And that's what I'm going to do here. Alright, we now need to know how to sample from this population that's being described in these couple of sentences here. So the first thing that's being described are these x's. We need to sample from 2 of these x's together. And we need to do it together because they're correlated. Okay? If the x's were known to be independent, we could simply say, we could do this. If we just went like this, x1 is r norm n, which is 50, and then we can say, you know, mean equals 0 and SD equals 1, and then we could do exactly the same thing for x2. Right, that would give us x1 and x2, and they would have the correct mean and the correct standard deviation, but the trouble with those is they would be independent of one another. They would have no correlation, and we've been told that we do want correlation. So if I were to grab this and run it, then we have an x1, okay, and we have an x2, and if we look at the correlation between x1 and x2, it's 0.3 in that case. So that's some randomness in the correlation. Underlying that correlation, there is the true correlation is actually 0. Let's see how we go if we run this again and get a different set of x's and y's. Different x1 and x2, and now the correlation is minus 0.06. What I did there, if that went by quickly, I've just ran the program again. Every time I run the program, I'm going to get different drawings for the x1 and the x2. So the first time I drew them, I got the x1 and the x2 that you saw printed out here, and I worked out the correlation between them, and I saw 0.3. And the first thing that occurred to me is, have I made a mistake? 0.3 seems kind of big for a correlation when I know that I've simulated them to be independent. So I went back and had a quick look at the program, and no, they're definitely independent. I haven't put any correlation in there yet. And so I just ran it again and got a new drawing from the population of independent x1s and x2s. And when I did that again, the sample correlation is minus 0.06, which is obviously closer to what we would expect from uncorrelated random variables. I could do it a third time. There we go, I just ran it again. And let's see what I get, plus 0.06. So those are looking like uncorrelated random variables. So that's all very well. The trouble is that's not what we want. Okay, what we want in this question is correlated random variables. Now there's a couple of ways that we can do this, or I guess many ways that we can do this. A very convenient way for us is to make use of a command in R that draws samples directly from a multivariate normal distribution. So that will allow us to do one command to draw both of the x's. We just need to know how to set it up. So we're not going to do this anymore. I'll get get rid of those two because they're independent, right? The command that we need is in, and I'll show you how to find help on this, is in the mass library, which comes installed in R. You don't need to install any new packages, you'll be pleased to know. So if I have a look in here, there is this mass library, MASS, which has this command mvrnorm. So if I'm clicking on that, this is how you can get help from within R, and it gives you the details here. The R help, incidentally, is not always the easiest to follow, and just equally often I just go to Google and type R and then whatever I want to do, and some readable help can be found online because R is such a popular package. There's always, Google will nearly always find you something. Anyway, this is what the command looks like. So a multivariate R norm is what this stands for, and it's got the same kinds of arguments as before, the sample size, so it uses mu for the mean instead of mean, and it uses sigma for the variance-covariance matrix of the variables. Okay, so the variance-covariance matrix, that's that kind of matrix that we talked about in the Good Friday lecture, at the end of the Good Friday lecture, where we specify the variances and the covariances of the elements into that sigma matrix. Alright, so here's how we're going to get this to work. First of all, this command is in this mass library. That's what that thing up there means. So in order to use it, I'll just put it up the top here out of the way. I'll just put in library mass. Okay, that means I can, if I don't do that, then R won't find this mvrnorm command. So what we can do is, well, let's set up this mu and the sigma squared. So the mu's easy. The mu is just going to be 0. Okay, so I'm going to set up mu of x, or the mean of x can be a vector of zeros. Okay, 2 by 2 vector of zeros for the mean. Now, for the variance matrix, what we need is a matrix that's going to look like this. Now, I'm just going to type some rubbish here. It's not going to be R syntax, but we kind of want this kind of matrix. Okay, so imagine that's a 2 by 2 matrix. We're told in the question that these x's should have variances of 1. Okay, so variance 1 there, variance 1 there. Okay, in this 2 by 2 matrix. Then we are told that the correlation is equal to 0.5. Now, normally in a variance matrix, what we would have on the off-diagonal elements here would be the covariance, not the correlation. But because both of these variances are equal to 1, the correlation and the covariance are exactly the same thing. So the matrix that we need to set up has this structure. Okay, 1's on the main diagonal and this row on the off diagonal. So here's how we can do it. We could set up a variance matrix for x, which consists of, let's say, we'll do it like this. We'll do it kind of column by column. So we'll set up the first column, which is 1 and then row. So here I'm setting up so that R bind 1 row is giving me this first column. Okay, the 1 and the row are getting bound together. And then I'll go R bind for the second column. That's going to be this row and this 1. Okay, row and 1. And then this C bind on the outside, this is binding those two columns together into a single matrix. Alright, so that's that. So I'll get rid of that rubbish there. Now let's just run that, and warning messages, I'm ignoring those. Let's have a look at mu of x, 0, 0 as hoped, and let's look at var x and 1.5.51 as hoped as well. So this would be, if you haven't already, this would be a good time to pause. Just type that stuff in, run the program, make sure that you can get that far and get your vectors and your matrices set up. Doesn't matter if you make errors along the way. I'm going to make errors along the way as I'm doing this as well, I'm sure. The main thing is that we get there in the end. All right, now that the mean and the variance, so this is going to be the mu of x, and the variance of x is going to be the thing here. So here is how we can draw a sample from this multivariate normal distribution for our x's. We can just go, and I'm only going to draw one, so let's not worry about the simulation for the moment. Let's just go x is going to be mv norm, just copying the syntax that's over here. N is our sample size, and then mu is equal to mu of x, and sigma is equal to var of x. Okay, and that should do it. So what that's going to give us is a random set of drawings in x. Okay, and there's going to be two of them. How do we know there's going to be two of them? Well, there's two elements in this mean, and that's where that command looks. This command will look at the mean and say, aha, you've got two means, that means you must want two random variables. And those random variables have variances and covariances specified by this matrix that we've defined here, and that goes there. Okay, so there's going to be two random variables, and they're going to be drawn from, those two random variables are going to be drawn from a total of n times, n being 50. So what we should get in x when we run this command here is 50 observations on two random variables. Okay, so let's do that, let's check. So I'll just run that. So far so good. Let's take a look at the x now, and that's looking pretty good, right? So there's our drawings from our x, starting from row 1 and going all the way down to 50. Okay. Let's see how we go if we go for the correlations of x. Now remember, we have specified that the correlation of x should be 0.5, and in this particular sample of size 50, we have got a correlation, a sample correlation of about 0.46. Okay, and the population correlation is 0.5. So that suggests that we're doing the right kind of thing. And again, we can do it multiple times just to get a feel for this. So I've just run the program again. That means we've got a new drawing from these x's, right? And I can go correlation x again and take a look, and now it's 0.64, so it's a bit higher than 0.5. We've only got 50 observations, so we'll get some sample variation. But it certainly does give the appearance that we are now drawing x's which are positively correlated, which is what the question is asking for. So we now know how to do that bit of the question. We know how to draw x's from the normal distribution with the specified mean, variance, and with this correlation. All right, what do we need to do next? We now need to get some y's. We've got the x's, now let's get the y's. So the y's are going to be drawn from a normal distribution with a mean given by x prime beta, where these betas are given by this standard deviation. Now again, there's a couple of ways of going through this. Just for clarity, I'm going to do the following. You don't have to do this, you could leave everything in a matrix, but I'm going to set up a single variable for x. So it's just going to be the first column of x's. So this set of numbers here, that's x1, that's our first explanatory variable. Okay, and our second explanatory variable, like that. Okay. And what that now allows me to do is just to very easily type in how I think the y's are going to be generated. So there's only one y variable. Okay, so we can just go back to our old friend R norm that we've seen before. So we're going to sample the y's, and our sample size is n, and the mean is given by the regression function. Okay, so the regression function has an intercept of beta naught, which is actually 0, so you don't have to put in the beta naught, but I'll put it in just to be complete about this. And then beta 1 times x1 plus beta 2 times x2. Okay, that's my regression function. The regression function is the mean of the y's, the conditional mean of the y's. And we also need the standard deviation for this R norm, which is given by this sigma, which we set to be 1 before, so that's sitting there ready for us as well. Okay. Now, obviously you don't have to specify these variables beta naught equals 0, beta 1 equals 1, and then type them all out again here. You could just put in, forget the 0, and you could just put in the mean as x1 plus x2. as a matter of programming practice, when you go back to look at this later and you want to check what you've done and understand what you've done, this makes things easier to read, to define yourself some variables here. It makes it easier to change as well. So if you define your parameters here and then give yourself some statements within your program that are easy to recognize and understand what they must be doing. So that looks like a regression function, doesn't it? So if you come back and look at this in another week or two and you've forgotten what you've done, but you look at this and you say, oh, well, look, it's a normal with a mean, like I'm doing a regression. Okay, you can kind of see even before you understand what's going on, what that must be. It makes things easier to generalize and debug and all of that stuff as well. That's our whys, okay? So that's all of our sampling process pretty much sorted. Why don't we just run this and take a look and make sure it runs? Yep, so far so good. Let's just check that we have some numbers in our whys. Yep, so far so good. That looks like some data. We could even, so we're going to run some regressions in our simulation. So why don't we actually run a regression and see what comes out. So let's just set up an equation, let's say, which is a linear model of y being regressed on x1 plus x2. And let's print that out, take a look. Now, what we're looking for here is a regression which looks kind of vaguely like what we might expect. Remember, we know what the population is here. The population is a regression function with an intercept around about, well, an intercept equal to 0 in the population, and these two slopes being equal to 1 in the population. So do we get sample estimates around about that? Well, we kind of do. So we've got an intercept of 0.1, which is, you know, a bit like 0, and a slope of 0.86 and another slope of 1.14. So those are looking like they're one-ish. Now, the reason for doing this, we're not doing the simulation yet. The reason is just, I'm just checking that what I've typed in seems to be plausible. If I did all of this and then looked at my estimates and they looked crazy, you know, if I got a coefficient on x2 of 100 or something, that would be telling me I've probably got a mistake and I better go back and check this before I start doing something more complicated like a simulation. So it's always a good idea to start just with one sample like this before proceeding on to the simulation. So as that wise econometrician Confucius said, you know, simulation of 1,000 replications begins with a single sample. On that note, you probably want to stop and run some of those lines yourself if you haven't already. But now we are ready to start building this little bit of code that we've got so far into a proper simulation that answers this question. We are asked to do 1,000 repeated samples, and for each one of those samples to calculate or to save the coefficient on x1, and then to get the mean and the variance and the histogram of that. Okay, so let's take these lines and start to create a simulation. In order to do that, we need to figure out which of these commands belong within the simulation and which of these commands are just kind of the setup commands. And it's easy to figure out. The lines that belong within the simulation are those directly related to the sampling, and these are the lines here in which we're doing the sampling, those 4 commands, and also the lines related to the estimation that we want to evaluate, which is obviously just this one. Now we're going to do 1,000 regressions. We don't want to print out 1,000 regressions, so I'm going to get rid of that. We're not going to include that as part of our simulation, but this block of commands here are the ones that belong within our simulation. So I'm going to set up a loop around those. Go back and check out the loopy video if you want to refresh your memories about how the loops all work. So our simulation is going to look like this. We're going to put in for j is in 1, 2 reps. Now I haven't defined reps. Remember, I started to define reps and then I stopped. Ultimately we want 1,000. I'm just going to put 5 just to get warmed up, right? because I'm just going to run a few, take a look, make sure it's doing what I think it should be doing, and then obviously bump it up to 1,000. So the reps start here, and I'm going to run down to there. All right, so we do our sampling in those 4 lines, and then we do our estimation. I'll just split those up. How about that? Just so that the steps are separate. You don't have to. These blank lines are just for readability. They mean nothing in R. Now, having done this regression here, we need to save the coefficient that we're interested in, which is the coefficient on x1 here. So I'm going to first of all create some storage for that, which is going to be a matrix, which I'll call beta1 hat. What you call it's up to you. I'll just call it beta1 hat. And that's going to be a matrix. And that matrix is going to have 1 row for every replication. So what we want ultimately is 1,000 drawings from the sampling distribution of beta1 hat. Okay, so obviously that's a mistake. I should have n row equals reps there. So the number of rows is the number of reps of the simulation that we're going to do, and the number of columns is going to be the number of statistics that I want to store, which in this case is just 1. Okay, I'm just going to store a single coefficient, the one on x1. If I wanted to store x2 as well, I could just put in columns equals 2 and store them both. Okay, so that's easy to generalize that, but we're just going to focus on x1 for this exercise. Okay, so we come down to here. We're now going to store the result of this regression, in particular this coefficient. So we're going to go beta1 hat, and which one are we going to store? Well, number j. So j is this counter, right? This counter is running from 1 up to, well, 5 at the moment, or 1 up to 1,000 in general. And so element j of this matrix is going to contain the equation coefficients number 2. Okay, why number 2? Number 1 is the intercept, and number 2 is the coefficient on x1. Okay, if I wanted the coefficient on x2, I'd put in coefficients number 3. Okay, so that's just going to store coefficients number 2, and that's it. That will do. Let's see if we have managed to write something that runs. Apparently so. Let's have a look at beta1 hat. There we go. We have now 5 replications. So we have 5 drawings from the sampling distribution of beta1 hat, and it looks like they're around about 1-ish sort of thing. You know, a few above 1, 1 below 1. There's no evidence here that we've made a mistake in any of the programming. Those numbers are making sense. Okay, so I'm feeling quite happy with that now. And it's time to bump this up to the full 1,000 replications. And the question is asking us to take a look at the mean of those. So we want to know something about the bias of this estimator, right? So we're going to print the mean of beta1 hat. So that's our simulation estimate of the mean of the sampling distribution of beta hat 1. Okay, so what we expect is that this mean will be approximately equal to the population value, which is 1. Okay, so this is an OLS estimator. All of our conditions for the unbiasedness of OLS are satisfied here. Okay, we have a linear regression function. We have IID sampling. So we know from the theory that OLS is unbiased. So the extent to which this number differs from 1 is just the simulation error, the fact that we're only doing 1,000 replications. We can also have a look at the variance, so how precise our estimator is. So sometimes we use a variance, sometimes we use the standard deviation. They both kind of measure similar things. Obviously, just one is the square. The variance is the square of the standard deviation. Sometimes it's nice to look at the variance, sometimes the standard deviation. In this case, we're asked to look at the variance. So we're looking at beta1 hat. I'm just going to print that number out and take a look at it. On its own, that won't tell us a lot. Okay, but when we get into the tutorial and start looking at a couple of different estimates, then we can start to interpret what this variance means. As we change the sample size or the rho or the sigma and that kind of thing, we'll see the variance of the OLS estimator changing, so the precision changing, and that's interesting. It's giving us a measure of the precision of our OLS estimator. And it also asks for the histogram, so let's just go histogram of beta 1 hat as well. We could put titles and labels and stuff like that, but we'll just type enough there so that we get a histogram to take a look. What we would expect to find, so what you know from second year, for example, is if the y's are conditionally normal, then we will find that these beta hats are conditionally normal. So what we'll be looking for in that histogram is a sampling distribution for the beta hats that's looking approximately normal, and that it should be centered at around about 1 as well. That's what we expect to see. And it's a good idea to stop and think, what do I expect to see from this program before running it, or perhaps after running it, at least stopping and thinking, is that what I think I should see? Because that will give you some idea as to whether you've written your program correctly and whether you understand the theory and all that kind of stuff. Okay, so I've done all that, and you might have noticed all this time I haven't saved it, which is not a real good idea, because if something goes wrong, I've got plenty of battery power, whatever, but if something were to go wrong and my studio were to suddenly stop, then I might lose my work. So this is, I don't know, tutorial 5 I'll call it. There we go. So I've saved that now. Let's run, see what we get. So it stops and it thinks for a short time, and then we get some output that looks like that. So here's a histogram as advertised. It looks pretty normal. It looks a bit squashed actually. Let's just expand it a bit. There we go. It looks a bit normal. I'll be happy with that. It looks like it's centered at 1. Happy with that. So that's pretty much what we would expect to see. No signs of errors in that. And here is our mean that's been printed out, 1.001. So that's pretty close to 1. That's what we would expect to see. That's kind of 1 within simulation error. Then the variance of our estimator is 0.0297. And that number on its own, like I was saying, we can't really interpret that. We can only, not on its own. What we can do is interpret what happens to this variance as we change things, which is what will happen in the tutorial. We'll change sample sizes and sigmas and this kind of thing. Now, before wrapping up, I'll just show you one extra thing as well. As I was saying before, when you rerun these programs, you get different sets of random numbers. So I'm just going to rerun it again. And you'll see what, by rerunning it, I've now got a mean of, instead of 1.0015, I've now got a mean of 1.0005. It's very close, okay, very, very close. And the same with the variance, 0.0297, 0.0291. So when we rerun this simulation, what's happening is we're going around this loop 1,000 times and drawing these multivariate normal x's and then drawing these normal y's. Each time through, we get different random numbers. Okay, we're getting a different set of 1,000 samples. Okay. Now, by taking 1,000 samples, we're getting 1,000 estimates of beta hat 1, all of which have a mean of 1. So when we take the average over 1,000 beta hat 1s, all of which have a mean of 1, we get a number which is very near to 1 in both cases, but they're not quite the same. There is nothing statistically or theoretically wrong with that, with getting different results every time you run the simulation, slightly different. Okay. However, there are sometimes, reasons why you would want to make sure that you get the same numbers every time you run it. One of them is if you're trying to debug a program, so you're not quite happy with what the program is giving you, and you want to change something and then rerun it and see what difference that makes. Now that can cause you a problem, rerunning a program when it's giving you different random numbers. So the trouble is two things change. You've made a change in your program, and then the random number generator makes a change on you as well. And then suddenly you're not sure, was it the random number that made my output change, or was it my change to the program which made my output change? You're not quite sure. And another reason to control your random number generator to give you the same set of 1,000 samples every time is replicability. And I use that feature all the time for our lecture notes, for example. So if I want to write a set of lecture notes and have the same sets of numbers coming out on the lecture notes and then on the overheads, and then when I run it in the lecture, let's say, then I can't have different sets of random numbers coming out every time I run the program, because then the numbers will be a bit different. Then I just get lots of questions about that, and that will just be a bit of a distraction. So there is a way to control the random number generator in such a way as each time we run this program, we will get the same set of 1,000 samples coming out of this process in here. And it's called setting the seed of the random number generator. So the seed is kind of where it starts from. The command for that is called set.seed. Usually you'll do that at the start of the program. Sometimes there are reasons for doing it later on in the program. What you don't want to do is to put this set seed command inside of your simulation, because then you'll just get the exact same sample every time you go through this loop 1,000 times. So then you don't get 1,000 samples, you only get one sample 1,000 times. That's useless. So make sure you set the seed. When you're doing simulations, make sure you set your seed out here somewhere. And then you have to choose a number. And the number that you choose is, well, it's random, it's up to you. So I just choose the most meaningful number I can think of. And what that means is now when I run this program, it's not running. Now when I run this program, there we go. Click on that. I seem to have broken my program. I told you that something would go wrong in here, didn't I? Oh, it was running. Look at that. I wonder what my computer was doing. All right. That's made a bit of a mess. Have a look at what's happened here. So I've run this program multiple times because the computer just sat there and thought for a while before it did anything. Here's the output that's come from that. 1.010 is this mean, and 0.0277 is this variance. Okay, those are those numbers there. And look, it's the same numbers there. If I run it again, there it is again. Okay, exactly the same set of numbers. So they're not changing now. Every time I run this program, I'm getting the same mean and the same variance. And the reason for that is every time it's going through here, it's choosing the same 1,000 samples of the y's and the x's. Okay, each of those 1,000 samples are different, right? They're all independently, randomly sampled as we want. But just when the program starts, it starts the random number generator from the same place every time. You don't have to use that, okay? That, like I said, that's not statistically or theoretically required, but it can be, on some occasions, a programming convenience to make sure that you're using the same set of kind of 1,000 samples every time. So most of the time in what I'm showing you, I will have that random number seed set, so I'm controlling the numbers that come out to be the same each time, so we don't have that kind of, well, literally randomness about the nature of the output. Okay, so the main thing from all of this is not so much the random number seed, that's just a minor thing, is for you to be able to follow through that sequence of steps that we went through in taking the information in this question and identifying the important pieces of those of the information in this question, and translating those into some lines of code in order to come up with a simulation. So I hope you have been able to follow this through and to arrive at a working piece of code that you can now take into your tutorials in week 5.